What you just saw is one of the key advantages of supercapacitors. And in case you're wondering, supercapacitors look like this, and I simply soldered a couple of them in series in order to create kind of like a battery pack that can be used in an uncontrolled way to melt metals or in a controlled way to spot weld metals permanently together. The advantage I'm referring to here is of course the power input/output capabilities of such supercaps, meaning I can discharge them through a huge current in a matter of seconds, and I can also charge them up very quickly. Other more traditional batteries like nickel metal hydride, lithium ion or lithium polymer can certainly not compete safely in that regard. So that should mean supercaps are the batteries of the future, right? I mean, they should be able to eliminate the long charge time of electric vehicles, for example. Well, sadly so far they are not super batteries, because the energy this one supercap can hold is about 30 times less than what this common AA battery can hold. That doesn't mean they're useless though, but their application as batteries is certainly limited. And that is why I was super excited to find out that there is a new kind of supercap on the market, called Lithium-Ion Capacitor. And needless to say, I got myself 3 of them. And in this video I will put them through a bunch of tests in order to find out what advantages they come with and whether they will replace traditional batteries. Let's get started! This video is sponsored by Skillshare, which is an online learning community with thousands of inspiring and useful classes. In case you don't know, then let me tell you that I'm constantly working on new projects. And as luck would have it, I recently had to get involved with a bit of Python programming, which I'm not very good at. But that is a perfect example of why I joined Skillshare, because they have classes on tons of different topics, including beginner courses for Python. Especially the course Python 3 Programming in Python for Beginners by Arkadiusz Wlodarczyk was a great introduction to the topic. And you can test this ad-free educational journey out as well by clicking the link in the video description. Because the first 1000 subscribers of mine who do so will get a 1-month free trial of Skillshare. So why not give it a shot? First off, let me tell you that I was a bit mad and confused about the excessive packaging the new supercaps came in. But after browsing through their datasheets, which I highly recommend you to check out if you're interested in all the details, it did make sense that each one got its own little plastic enclosure with the leads being physically separated. This is, by the way, a big difference to the packaging of other capacitors. And the reason is simply that these lithium-ion capacitors, or LICs, which will be the abbreviation I will be using from now on, are pre-charged to a voltage of around 3.5 volts. That of course means that when the terminals touch, a big short circuit current will flow. And that is something the manufacturer does not want. But we will try that out later. But I'm getting ahead of myself, because before that we need to find out why exactly LICs are pre-charged. And for that we simply have to learn about the composition of LICs, which are a type of supercapacitor called hybrid capacitor. And hybrid explains their structure pretty well, because while their cathode is the same as in a normal supercapacitor, their anode is the same as in lithium-ion batteries. So in theory, that should combine all the advantages of both energy storage devices, but sadly also partly their disadvantages. You see, discharging lithium-ion batteries underneath 3 volts is always a no-go, because underneath this voltage chemical processes take place that reduce the capacity of the battery over time, which means it cannot hold that much energy anymore. That is also why there exist tons of circuits that prevent such an over-discharge. Now LICs have a similar problem at a threshold value of 2.2 volts. But then again, due to the lithium-ion technology, their voltage limit is at 3.8 volts instead of the common 2.7 volts for normal supercapacitors. And since the voltage limit directly determines how much energy a capacitor can store, the LICs should be capable of storing more, right? To properly determine that, I chose a 100 farad capacitor of both types and calculated the energy they could store, while keeping in mind that the range for the super one is from 0 to 2.7 volts and the LIC one from 2.2 to 3.8 volts. And with those results alone, we can already see that the LIC stores slightly more, while being a bit smaller in size. But to properly compare the capacitors to the traditional batteries, I next had to determine their weight and volume to calculate their gravimetric and volumetric energy density. And here you can clearly see that the LICs have the advantage, with a doubled value for the watt-hour per liter value. But then again, if we include those values into the traditional batteries graph that I created during a previous video, we can see that even the newer capacitor technology stands no chance against the more common batteries. And that basically means LICs will not be battery replacements, but they can work wonderfully together. Let me explain in the next experiments. According to the datasheet, my LICs feature an internal resistance of 100 milliohm to 50 milliohm. Which once again means you can charge them up super quickly and you can also discharge them quite aggressively. By the way, during this power input/output tests, I purposely ignored all the warnings given by the manufacturer concerning max currents and such, because I wanted to find out whether the LICs can take a beating while working flawlessly. And after doing 5 rounds of discharging the cap down to 2.2 volts and charging it up again, it was pretty clear that this technology can not only output big current spikes, but it also didn't lose any capacitance while doing so, and it only heated up slightly during the whole process, which were all positive results. That means LICs could work well together with batteries as buffers in energy systems, in which quick charge/discharge actions take place, like maybe in an electric vehicle during regenerative braking, or in an uninterruptible power supply with big current breakdowns. But if you however want to use LICs as the sole energy source, then I can only recommend them for the following applications. Firstly, for devices that need to create a stable voltage through comparable low input power. Secondly, for very low power devices that should run for years, like IoT devices, because LICs not only feature a low self-discharge in comparison to normal supercapacitors, but they can also be charged up and discharged thousands of times without losing capacity, which is a big plus in comparison to other batteries. And lastly, for devices in a very harsh environment, either temperature-wise or safety-wise, because even though LICs can input and output power very quickly, they are a lot safer to handle than other lithium-based batteries, as you can see here. If your device fits one of those criteria, then the LIC is for you. Assuming you can swallow the huge price point at the moment, which once again compared to the other batteries is huge. But anyway, my final verdict for lithium-ion capacitors is mixed, because on one hand they do improve the supercapacitor technology quite a bit, but then again, implementing an over-discharge protection for such a high current energy source will be super annoying. But what do you think? Let me know in the comment section below. With that being said, if you enjoyed the video and want to see more, then consider supporting me through Patreon. As always, don't forget to like, share, subscribe and hit the notification bell. Stay creative and I will see you next time!